first, this is the third bit, and I should just very quickly say that not only Maxime has been a very good friend for me very many years already, but also that he has been a relentless supporter of Latin American and Mexican mathematics. So he has been absolutely have never spared energy or support for Latin American mathematics, and INSA would not be possible without his constant support of many mathematicians, more recently Leonardo, for example, and many others. So, of course, I have stories, but I'll reserve for the occasion. And now I'm going to try to go fast and impressionistically because although there's a lot of details on the slides, I will just give kind of a bird's eye view of the story so that you take something home and we finish earlier today, hopefully. So I'll just go very fast. If you see many tests, I'll just try to say in words what is going on in this story. So this is joint work with Ludmil Katzarkov, Kyoung-Seog Lee, that is over there, and Laurent Meersseman at Angers. Kyoung is at Postec and Ludmil Quantum States. So, both here in Miami, director of INSA. And so, I want to talk about Hodge numbers of non-algebraic, actually non-Kähler complex networks. There is this very, I mean, Hodge theory has a lot of pedigree, and there is this very famous work of Pierre Delin in these very famous papers, Hodge 1, Hodge 2, Hodge 3. And a lot of these stories, how to go about, but that theory is definitely being developed for Kähler manifolds at least, and we have been developing the story for non-Kähler manifolds. This story of the Hodge theory for non-Kähler manifolds. So, but let me tell you more or less the story, how we came about studying this thing. And it really started in earnest at Alberto's birthday in Mérida, Yucatan, where the four of us were there for your birthday conference. And then we started and said, well, this and that. And then we thought that it would be nice to understand a little bit these manifolds that are very, in Latin America in many ways, the LVMB manifolds. That started, Alberto is here, he's the institution, he can tell you the story. But they started at a seminar that Alberto was had at the university. And then he and Santiago Lopez, the Belgrano B. Verhofsky, started studying some aspects of dynamical systems related to foliations and so on. And then they came about discovering this large family of non-Kähler manifolds that have many nice properties and that they were very interesting to study. They are connected to many subjects in mathematics. So Alberto can really talk about that in detail. He's probably the person that really was the first to have an inkling that they were there. And then they brought them to the foreground. And so this theory, one way of seeing this theory is kind of in parallel to toric geometry. It's kind of a non-Kähler toric geometry. It's kind of a non-Kähler toric geometry. Just like toric manifolds, very small manifolds, are equivariant compactifications of complex tori. LVM manifolds are equivariant compactifications of possibly toric cross affine is abelian complex Lie groups. So you take these abelian complex Lie groups, don't need to be toric, it could be a toric cross CM, vector space CM, that's an abelian group. So you could have this kind of group that is not necessarily a toric, but it's still abelian. And now you compactify, or partially compactify, and then you would be doing this LVM theory that clearly kind of has the flavor of toric geometry, but it's slightly different. The outcome is most often than not, and this stuff is very, very related to Maxime Stock's model. So I will also try to point out what it contacts with all the story of Maxime. This provide a factory of examples for Maxime's investigations this morning. Factory of them. And by the way, there is this kind of geometric combinatorial data in vectors in CM, and then you ask for conditions, or two open conditions. One is the Siegel condition. 0 belongs to the convex hull of the vectors. And there's the weak hyperbolicity conditions. You are not in one of those lines. You don't want to be in one of those lines. And the origin should not be in one of those lines. There's chambers, and you cross chamber, there's wall crossing, but let's just fix chamber, and we have this kind of situation where you don't touch those lines. And the origin is inside the polygon, the convex hull of the complex numbers. That's the input data. This slide is the input data. And then you do something that will be very familiar to you if you have done toric geometry. You just with this data, you form this kind of Cox-like construction of the LVM manifold, where you produce this big open set of Cn just by the combinatorics of the subspaces generated by these things, just like in toric geometry. And then you produce an action of a group, but observe that this group seems to be CM, not a torus. But of course, once it comes down to it, it ends up being the product of a torus, because some coordinates of this CM wind on themselves, and some don't. So it ends up giving you the compactification of this abelian complex Lie group, complex abelian Lie group, if it is a torus. It would be a toric variety, but otherwise it would be something else. And it is LVM that are described here. This is the explicit action on the productivization of this open set, and the quotient gives you the LVM manifold. There is a slightly more general situation, and let me not say much about it. It's even more elaborate. The combinatorics is even more elaborate, it's more general. And we really need this level of generality for what I'm going to say, but let's ignore this additional layer of combinatorics. So the point is that you will end up with a lot of manifolds, and either you get a compact complex torus, the simplest case, but this is the case that was mentioned in Maxime Stock, or a non-Kähler manifolds. And the same with the other slightly more elaborate situation. You get a compact complex torus or all these large family of non-Kähler manifolds that are compactifications of these groups. So so the point is that C star n acts on S with an open dense orbit, make it into a toric variety. This open set is a toric variety. This action commutes with the productivization, and therefore the manifold given by this datum is an equivalent compactification of an abelian Lie group. Okay, and of course, just like you have in traditional toric maps, you have these kind of maps that are equivalent with respect to the action of this dense abelian Lie group. So it's almost amorphous in the group, but then you extend it to the. And that will tell you how to compactify this abelian Lie group. That is not necessarily a torus.
But once you have this manifold that is non-Kähler, not symplectic and not Kähler, you still have a moment map. You still have a polytope, just like for total varieties. You still have a map to this polytope, and this map, you can think of it as a moment map, even though you don't have symplectic form or a Kähler structure or anything like that. This map still maintains a lot of properties that a typical moment map will have. Which ones? Well, you would have to see the details of the theory. But now something very nice happens. That is that just because it is this equivariant compactification, then this manifold knows, because of its symmetry, it just carries a totally canonical holomorphic foliation. So these manifolds are these manifolds, but they are just not these manifolds. They carry a canonical foliation. If you just give me a complex manifold, I can immediately produce the foliation, because I just look at the symmetries of the manifold, and then I'll read off the foliation. So the category of these manifolds with this map that I described are really, they really know their foliation. If you give me this naked manifold, I can instantly put the foliation back. So it knows its foliation. So it has this foliation, and this foliation either is rational or not rational. And this is something very similar to what happened with the quantum torus. You have this canonical foliation of the torus, and this foliation could be rational, and then the leaves of the foliation are themselves tori, or not rational, and then the leaves are these CMs, non-compact, but they wind densely along the torus. Here, it's exactly the same pattern. You have this LVM manifold. It has this foliation that it just knows the LVM manifold with its complex structure. And the complex structure knows whether it is rational or irrational. Just the complex structure knows this. And if it is rational, it winds on itself along abelian varieties, CM modular lattices, and of the right rank. And if it's irrational, it doesn't. It just goes, but some leaves are still tori, but most leaves are based somewhere, maybe not everywhere, but somewhere they just wind densely, these leaves, most of the leaves. So rational, all of a sudden, it's all these leaves are tori, and irrational, they are not. They are bends everywhere, and the quotient non-Kähler. And again, non-Kähler is mentioned very much in Maxim Stock remark. It's the same kind, exact same kind of non-Kähler. And there is this very beautiful theorem of Meersseman and Verhofstadt that says that in the rational case, the complex structure knows this. So you just give me this complex manifold. And then the complex structure knows if it is rational. In that case, the quotient is exactly the category, it's a total variety, and all of the total varieties are this way. So it is bad. You see, the leaf was winding on itself. So this winding on itself gives, the quotient has stabilized there everywhere. And this is the germ that appears, the germ that appears in Maxim Stock. This stabilizer everywhere, it's the quotient's a total variety, or you prepare a total variety together with a germ. And it turns out that the category of total variety is equivalent to the category of these total varieties with the germs. So you can forget the germ, but you may not want to forget the germ to have the right deformation parameters as in Maxim Stock. To have the right deformation parameters as in Maxim Stock, you want to keep the germ. So you have the total variety together with a germ in the theorem of Algato. So
if this X, it says update now. No.
Don't update, please, Microsoft.
So you have this toric variety here. So the typical picture is this: toric variety, rational LVM manifold, and the fiber is some sort of, for example, if it was P1, here you have the Hodge surface, and here you have an elliptic curve, and you would have an elliptic fibration. So you can talk, another way to think about these LVM manifolds, another way to think about these LVM manifolds, as we prove in our paper, is a generalizations of elliptic fibrations. But for these are not only elliptic curves, but more complicated abelian varieties. So you have this toric variety, but this is only the rational LVM manifolds. What happens to the irrational LVM manifolds? What has to be here is a quantum toric variety. And now, of course, you can vary the complex structure and it becomes rational. Now, observe that the C-infinity manifold doesn't change. And as you vary the complex structure, rational, etc., you vary the moduli, you produce the modular space of quantum toric varieties. And it is a theorem of Laurent, Alberto, Ludmil, and me that this modular space is a complex order and can be studied, it has topology, etc. So this is the modular space of quantum toric varieties. The rational forms of this modular space are the classical toric varieties, and then the irrational forms of this modular space are the ones that are these kind of non-Kähler stacks that Ludmil was mentioning. And this is a non-perturbative deformation theory for toric manifolds. So they have the rates of function and everything, and it fits with what Maxime was talking this morning. So it's a totally non-perturbative deformation theory in the toric case. But of course, pick your poison. Either you do this deformation theory here, as Maxime was doing today, or you vary the complex structure here. But when you vary the complex structure here above, everything is non-Kähler. So pick your poison, non-complex spaces or non-Kähler spaces. Now, you lose algebraicity. These non-complex spaces remain Kähler all the time, but the ones above become all non-Kähler. So, again, pick your poison. You want to study non-complex geometry, or you want to study this non-Kähler geometry? You want to study this Hodge theory or this Hodge theory? We're going to study this one here, the Hodge theory of non-Kähler manifolds. Okay, so that's the story.
Alberto, did I say this more or less? Yeah, okay. So a nice example is this one, this Hodge manifolds. Hodge and Kähler manifolds, and Alberto proves that the formations of these really are almost everything, Hodge manifolds is you take these lambdas, these ones, the ones that I write down here. And then you end up with the equations, and when you do the thing, you end up with the Hodge manifolds and with the Hodge surfaces for n equals 4. So for n equals 4, this input data gives you this output. And more generally for n larger, well, you get these product of spheres that could be thought of as Hodge manifolds. Okay, but now you have those data, and now it's important, just to illustrate what we're going to see, that we could add additionally more lambdas in the form I described here, and then all this will give you manifolds that are diffeomorphic to the Hodge manifold cross at real torus, but they have a vast number of non-Kähler complex structures. In fact, quite C-infinity, there's a map from this to this, that is the projection. There is no such projection holomorphic, analytic. The complex structures are not compatible. And also, as I vary this lambda that I just wrote in that matrix, I vary
in the formation class of the non-Kähler complex structures so these manifolds are a lot of complex manifolds, very many different complex manifolds. Also topologically, these manifolds that I just use the Hodge cross many circles and even number of them. Or you can do the same for the Calabian.
By adding more lambdas, you can do the same for the Calabi-Eggmans. All these products of spheres over projective spaces. And then you can also product times S1 times S1 times S1 times S1, even number of times to be even dimensional. And you get all these complex manifolds, and they are not related as complex manifolds. They have C-infinity maps, but they are not related as complex manifolds. This one is not the product of these two complex manifolds in particular. Namely, here, you don't have that this manifold here is a product of these complex manifold times this complex manifold. No, is these very elaborate complex structures that encode, if you want to see downstairs, a complicated structure of a non-commutative space. That is a deformation for positive H bar. So, well, that's the thing. Just a recap, LVMB manifolds are non-Kähler, compact complex manifolds. They generalize LVM manifolds. The input data is this n total of vectors that satisfy certain combinatorial relations. And we obtain the LVM manifolds as a coercion of the productization of the complement of some subspace arrangement by an explicit CM action. And the subspace arrangement is encoded in a simple convex polytope, the moment polytope of the manifold. This is a recap of everything I said so far. That's it. Okay, now, the purely topological properties of N were brilliantly studied by Bosio and Meersseman, and it's a beautiful paper in ACTA, and they can be written down. It's an extremely elaborate story. But they depend on the arithmetics. But now we want to study not the purely topological properties, but the complex analytic properties. So let's see what we want to see the Hodge number. So we want to see what is the Dolbocco homology. So the Dolbocco homology, HPQ of N, this is better understood for Kähler manifolds. It's a refinement of the Ramko homology. However, this connection no longer holds very well in the non-Kähler world. The Hodge polynomial of a rational LVMB manifold is often computed by applying the Borel spectral sequence. But it's not very explicit, this calculation. This is Panov and Ustinov have this nice calculation, but it is unfortunately very complicated, not very explicit. The spectral sequence is complicated. And this is only for the rational ones. You cannot apply the spectral sequence to the non-rational ones, of course. The absence of a Kähler structure makes it unclear whether the resulting Hodge numbers are topological invariants. The Borel spectral sequence failed to yield results for the irrational ones. In particular, we don't have arguments based on density because we have only upper semi-continuity, and they are not in general deformation invariant, the Hodge numbers. And also this spectral sequence makes very opaque the relation to the combinatorics of the moment polytope. So we prefer a more direct and explicit computation that can be performed for every n. So these methods that people have used, it's only for the rational, has some shortcomings. Our method does a little bit better with this. And well, we do the calculation. This is a kind of an elaborate spectral sequence calculation that is kind of a balancing act between some
check to those both spectral sequence together with the prolix spectral sequence. So you have usually distance between the prolix spectral sequence and the differential and the check to those both spectral sequence, and then you get the answer. So I will not torture you with the diagrams or anything like that. Let me just say that out of these diagrams, for example, if just the polygon was a polygon in dimension 2, let's write the formula for a polygon in dimension. Observe that for toric varieties, we know that then the dimension of the toric variety is 2 complex dimensions or 4 real dimensions. But here, not quite, because we could have all these lambdas there in the same dimension that like Mark points. If you have attended my quantum geometry talks, you know you can have this quantum found with Mark points and so on. And then the result is that here we could have arbitrarily large dimension LVMB manifolds, even just for polygons of dimension 2. So any dimension we can have, even just for polygons of dimension 2. But in any case, it turns out that a combinatorial number appears in our formulas that is SL. That is that number, the number of these opposite sides of the polygon. So you call L the number of opposite sides on an L-sided polygon, and that you call that SL. And this number appears all over our formulas. So that's the main combinatorial input from the moment polygon. And this is the formula. And it's not very simple. But these are the Hodge numbers of these manifolds, of the LVMB manifolds. And it's an elaborate formula. So what are we going to do with this formula, and what does it mean? We wanted to know, what does it mean? We were thinking, what does this formula mean? I think we figured out what it means. So let me tell you what it means. So it is a mouthful, you know, it is a mouthful, this formula. I couldn't even make it fit in one line, so I had to cut it into formulas, you know, because it's a long formula. And it's very combinatorial. It's very combinatorial. It has all these binomial coefficients. So let's take, for example, just the quasi-Hopf manifolds. This is even simpler than this situation. For the square, it would be the Calabi-Ekman. But for the quasi-form, it's really in dimension 1, it's just the interval. And we get this formula, the same kind of formula for the interval. So what's going on? Well, you can notice though, if you start computing these numbers, you know, it's easy numbers formula. But now you compute the numbers in cases. And then remember, you get this S1 cross S1, S1 cross S1, S grand cross S1, as you are topologically, complex arithmetically complicated. But you have these numbers, you get this S1 cross S1, S1 cross S1, S1 cross S1 for the same amount of polyton as you mark more points. And you just put the numbers and compute all these elaborate combinatorial formula for L equals 1, L equals 2, L equals 3. And it turns out that you get the Hodge diamonds, of course. You put this Hodge diamond, and the next Hodge diamond here, and the next Hodge diamond here, and the next Hodge diamond here. And what you realize is that it's a Hodge Pascal pyramid. The 4 numbers here add up to the one here. And then the 4 numbers here add up to the one here. And then the 4 numbers here add up to the one here. And so you get this Hodge. So all these LVMB manifolds land in these Hodge Pascal towers. So this was, I mean, a bit of a wild guess, but it was to be expected because all this is a quadratic expression in combinatorial numbers. So that. And then you realize that you can prove by induction, but of course but you can prove by induction that this is true. You have a recursion problem. So you can prove that this pyramid, this Hodge Pascal recursive relation holds. In this formula that I wrote, in that case formula, you can prove that it's holds. It's not pretty, but you can do it, you know, by induction. Okay, so you have that recursion.
And now you say, well, but combinatorial all the time you're generating polynomials. So I'm going to try to collect these coefficients in a two-variable polynomial so that I can do something with it. So this is the most simple generating function for combinatorial numbers, this thing that appears all over the place in this formula. And, well, it already motivates you to write the generating function for the Hodge numbers. These are Hodge numbers, aren't they? And they look like highly combinatorial entities. So I'm going to write the generating function. I'm going to try to write the formula that generates these horrendous numbers, because I want to understand. So I write the generating polynomial. And this polynomial already has a name, by the way. We were motivated by explicit calculations, but it has a name. It's called the Hodge polynomial. But this is called the Hodge polynomial for algebraic or Kähler manifolds. Unfortunately, it's not called that for non-Kähler manifolds, because it would make you believe it has nice properties, and it shouldn't have nice properties. There's counterexamples to nice properties, so you should not call it that. Nevertheless, we call it that, the Hodge polynomial. And for algebraic, for Kähler manifolds, it has very nice motivic properties. This is a theorem. And to prove this theorem, you really need the full force of the being Hodge 3. You really need the whole thing to prove these properties. You really need the whole thing to prove these properties. So it's not trivial, but it's true. So these are the motivic properties in the algebraic case for Kähler, but these are non-Kähler manifolds. And there are counterexamples to this in the complex analytic case. There is non-Kähler. Counterexamples to this. Easy counterexamples to this. And so, nevertheless, one can write all those combinatorial numbers like this. Just like that. That's the polynomial that generates those numbers that I. Now, how do you guess this polynomial? Well, you do things. You do what you can. You use the theory of Gauss hypergeometric functions. I'll explain it. So, by the use of the theory of Gauss hypergeometric functions, you can obtain this polynomial. And that's the same formula as the other one that. And again, this number that I have to separate, I have the formula is so large that I don't tell you what P is in this one. I only tell you what P is on this one. And is that summation of hypergeometric functions. But then you use the theory of hypergeometric functions and a miracle happens, becomes a polynomial. And of course, it's full of miracles, this story. It's impossible, this story, you know. All these numbers are rational numbers. But the outcome is a polynomial with integer coefficients, we know. So this already gives the students in the undergraduate degree truckloads of combinatorial theorems for polygons and things like that, that are impossible combinatorial identities. Impossible combinatorial identities are a corollary of this step, of this remark. So these miraculous combinatorial identities are, but you know, using the theory of hypergeometric functions, you prove that it's a polynomial. So this is a polynomial, and this is a nice polynomial formula. Very nice polynomial formula. Well, in the case of quasi-Hopf manifolds, it's small. You simplify further and further, and you get nice small formulas. And then you start realizing that if you introduce the polynomial of that minus the polynomial of that, and now you call it in quotation marks that minus that, big 1 cross E minus the Hopf surface, and this object doesn't exist. You see, there is a nice K0 bar motivic ring of algebraic varieties or Kähler manifolds. But there is not a nice, there is just not. We know there is not a K0 of complex manifolds. It's set, you know, it's nothing, you know, because K0 of complex manifolds only behave like algebraic manifolds. So you're putting quotation marks this P1 cross E minus H. But it turns out that this one polynomial is all that is not algebraic in all these formulas. And this is exactly like what you do to realize the Hodge surface, that is an elliptic vibration, as a log transformation of the trivial elliptic vibration. You have the trivial elliptic vibration, you do a log transformation, and you get the Hodge surface. And the difference between the trivial elliptic vibration and the Hodge surface is this object, that is this polynomial thing, that is not symmetric, of course. It doesn't have any chance of being algebraic, but that nevertheless is the thing that is giving you all these formulas, in particular, the simplification of the hyperelliptic formalism here. So you do that, and then, well, but now you say it feels as if I was living in K0 bar, so I just go with it. And you know, there is this theorem that again uses the full form of the Lee tree, that there is K0 bar to K0 Hodge structures, and then you have this a so-called motivic measure. You know, it's a real homomorphism from K0 bar to K0 Hodge structures, and from them to the integers, giving you the Hodge numbers. And this is a kind of a universal morphism of rings. Well, if you keep playing with this, you obtain this kind of formula for the quasi-Hopf. Remember, the quasi-Hopfs were this Hopf topologically crosses one, crosses one, crosses one, crosses one, crosses one, crosses one. And they have no hope of being biholomorphic to H crosses one, crosses one, crosses one, crosses one. It was just topologically. Nevertheless, motivically, they look, well, the Hodge polynomials look the same. And then this suggests that if there was a motivic ring, these two things would differ by 0 divisors. So, and this formula, this extraordinary combinatorial formula satisfies, it's unbelievable, this formula, crazy formula, satisfies exactly this condition. So it's this formula, the induction of the Hodge, the Lee theorem is equivalent to this condition. So sounds have been two miracles. I don't know, I mean, how come the combinatorial formula has motivic properties, even though there seems to be no motivic ring? The same for the Calabian. Well, also the fact that this really has no hope of being clear and right or anything, they really are the outcome of this pluri-logarithmic, what we call the pluri-logarithmic transformation. We have this pluri-logarithmic transformation. This is the outcome. No hope of being Kähler or anything like that. So this is really the non-Kähler world. Well, let's see what we can do. So there's yet another problem. For Kähler, there is one notion, you know, of this kind of HPQ. But now we have many notions that diverge for the non-Kähler case. We have the Dolgov homology, the Bot-Cherenkov homology, the Aekikov homology, and they are all different in extremes. So they are. We also have that problem. You know, there's all these new features coming in, confusing you. Well, what we do? Well, this is what we do. We say, well, there is no hope of having a motivic ring for complex numbers. But why we restrict our attention to a much larger family than algebraic, Kähler manifolds, much larger than algebraic, but not quite all complex numbers where we know this cannot possibly work. Well, there is a family in between. We can take from mathematical logic the concept of O-minimal structure, and we can impose it on the category of complex manifolds that we can study. And so there is this kind of quantifier elimination procedure that can be written geometrically if you prefer. That's
what you would like to do. But it's a matter of encoding in geometry the notion of quantifier elimination. So, algebraic geometry works because there is these letters that move, and there's this symbolic game, and then you do things. But many theorems in geometry, as the Oxford School of Kyoung-Seog Lee has shown, have another proof, completely different proof. It's very simple. You do this, you say, no, it's not because you have this symbolic game of letters and algebras. It's because you have this quantifier elimination game. It's another game, it's another video game, it's another formal thing that is very different. And you need an proof. You need an proof. There's more objects here than here. But the theorems, systematically, you prove them here, and a lot of them remain true. So with this kind of logic game, in the minimal structure, so there is this theorems that have this algebraic proof. Here, you have to abandon cohomological methods, which is very hard to do for the human mind, you don't have a lot of these cohomological methods. It's a new game, it's a different game, yet many theorems remain. So you do that. It's a very different way of thinking, very, very different way of thinking. And, and an all minimal structure has sets. And again, it starts with the real numbers. It seems to have nothing to do with the complex numbers. And this is also extremely possible because the things I'm going to say are eminently in the complex universe, in the holomorphic universe. So it all seems odd at first, but anyway, you have all these sets. They form a Boolean algebra. If A belongs to the family of sets, A cross R belongs to the family of sets. The diagonals belong to the family of sets, the projections, the singletons, and the less than equal things. And R1, very important, consider finite union of open intervals and points. And this is called a non-minimal structure on R. And there is deep theorems here. It is a very deep theorem in logic that R and X is a non-minimal structure. And it's very interesting because a typical non-minimal structure is more or less algebraic geometry, semi-algebraic sets, and they are a non-minimal structure. That's people on this universe would say that's why algebraic geometry works. Other people would not agree with that statement, but that's why algebraic geometry works. But now we can include the real exponential function. This is miraculous. This remains a non-minimal structure, and this theorem is highly non-trivial and very beautiful. And so this is kind of and then you can add some packets a little bit more, but this kind of the minimal structure, the universal minimal structure in the universe, and now you can take these exponentials. And it behaves like algebraic geometry, even though now you can take these exponentials. So you do that, you have many more functions than just algebraic functions, many more. And Petersil and Starshenko, in a famous paper in a famous presentation at ICM, presented the extension of complex analysis to this universe, and in particular proved that any complex manifold is definable with the minimal structure. Any complex manifold is definable with the minimal structure. And now we're in for a little of a surprise. Because, well, you can use this, you can talk about compactifications of analytic spaces, You can take two complex analytic spaces, etc., etc. And so you have this important counter example, two compactifications of open complex manifolds do not need to be by meromorphic. And it's very easy. We already have an example in our calculations. We have the call that is the log transformation of the trivial elliptic vibration. And this gives you a counterexample. This difference, this famous different thing, should not be zero in your purported universe. because it was this crazy polynomial that was non-symmetric. So that violated
PQ equal QP. And so it is one of classical problems in complex algebraic geometry, analytic geometry, to compare different compactifications. Nevertheless, we can prove in our paper, that should be on the archive any minute now, that E1, U1, and U2 are definable open subsets of compact complex manifolds, and they are isomorphic in the minimal universe, then they are bimeromorphic. And now we can fly. With this, we can define.
So how does this, can you explain like this, how this page to apply to the example before?
This other thing was not definable. These pieces that we were cutting, the thing were not definable. Yeah. So you have to cut to do the sister relations in the definable world. You have to do the sister relations in the definable world. And now you have a nice K0 depth. A nice motivic ring, a K0 depth. This one is nice. It's not K0 complex manifolds, which is nothing. It's K0 depth is now a nice ring. Thanks to these lemmas. And we can prove Bittner's theorem. But now it's a bit striking, this theorem, because half of the theorem never mentions definability, and the other half does. Now it's very striking, you know? You define the Bittner ring of complex manifolds, you know, with compact complex manifolds and manifolds of compact manifolds that are compact, etc. And now you define the Bittner ring with the Bittner relations. That's one ring. You define K0 depth with the definability in the O minimal structure, this O minimal structure that uses the exponential complex. And more importantly, the locally analytic functions. And now they are the same ring. It's magical, you know? I mean, it's very striking because one side doesn't use definability and the other one does. But it's true. And so we have this isomorphism, this Bittner theorem for the definable K0 depth, where K0 depth is isomorphic to the free abelian group generated by isomorphism class of compact complex manifolds modulo the blow-up relation. That is striking. Now, now we can define motivic measures, and because they were Weil cohomology theories, all of them, the Ram, Apelli, Botchern, and Dolbeau, induce various motivic measures of vision. All of them induce motivic measures of vision. So you have all of these motivic polynomials for the and particularly for compact complex manifolds, not necessarily Kähler. Like the ones we were working with, the LVMB manifolds of the story. We also have this Larsen-Lutz-like theorem, but now it's not by rationality, but by meromorphic classes of compact complex manifolds are K0 depth modulo the Tate motif. And then this gives away a little bit of the structure of this K0 depth. You typically have this birational geometry thing, but now you have this by meromorphic classes of manifolds. So this generalizes Larsen and Lutz, and in Larsen and Lutz the B would be irrational, and in our universe is bimeromorphic. But now there is a log transform. In the algebraic world, we didn't have the log transform. And now this produces troglogs of zero divisors. And this is probably, we conjecture, very intimately related, Ludmil especially, to the phantom category phenomenon. But even just at the motivic level, you didn't have the log transform in the whole world. Now you do. There was no code in the algebraic world to do this kind of thing. But now you do. And now you have troglogs of zero divisors in the motivic ring, which is very intriguing.
So we have a theorem.
Logarithmic transform is a factory of zero divisors. And here we use generalizations of the Jacobians to higher dimensions and so on and so forth. As Laurent very expertly has, Kyoung as well, have thought of this story. In any case, we can ask what are all possible Hodge diamonds in this universe. And it happens to be the case that in characteristic P, Dobben, but building on work of Serre and Kostic and Schreider and so on, even Serre 1958, they, in characteristic P, they know that is a free algebra on 3 generators. This mysterious object E of Serre that doesn't exist in characteristic 0 algebraically. It does not exist as an algebraic variety in characteristic 0, but it exists in characteristic P. And so you have these 3 things and they generate all possible Hodge diamonds. All possible Hodge diamonds come from these 3 things. And our theorem that generalizes a theorem of Stelzig for compact complex manifolds. Now for the final, all the Hodge diamonds is the same theorem in characteristic P. But because now we have the Hodge manifold, and we knew that was the only thing that was giving us all the polynomials. These louder formulas. It's so we have now that this mysterious object characteristic P by Serre in the complex domain characteristic field is the Hodge manifold. It has no hope of being algebraic. That's why we were losing it. But now we have it. So we have the Hodge manifold, and we have that. Those are all possible Hodge diamonds. And and finally, final remarks. The definable Chow theorem of Petersil and Sarshenko states that in a closed analytic subset of Cn, which is definable in a non-minimal expansion of the order field R, is necessarily algebraic. So yeah, you have this thing, and then you have this final thing, but you know the big thing is algebraic. The definable thing is algebraic is called this Chow-like theorem of the logicians. So they have this logicians Chow theorem. And the result has been a crucial tool in several recent developments in Hodge theory. It played a pivotal role in the work of Baker, Klinger, and Zimmerman, which provided a new proof of the theorem of Catani, Deligne, and Kaplan on the algebraicity of the Hodge locus, as well as in the work of Baker, Brunapard, and Zimmerman, which resolved a conjecture of Griffiths on the algebraicity of the image of the period map. That was a key component of that story. We, using the definable Chow theorems and our generalization of Widmer's theorem, will show that there is a morphism from K0 var to K0 depth. And the image is a proper subring. For Kähler manifolds, a modification may not preserve the Kähler property, but will place the manifold on the Fujiki class C by definition. According to characterizations by Demey, Lee, and Pong, membership in this class can be identified through the presence of Kähler kernels. In contrast, other classes in the Widmer ring consist of non-Kähler manifolds that are non-bimeromorphic to any Kähler manifolds. Examples include Hoff and LVMB manifolds, just to close the circle. Of particular interest is the observation that an equivariant compactification of a abelian group, as in the case of LVMB manifolds, belongs to Fujiki class C if and only if these 2 Hodge numbers are equal, which is not always the case. So we really are out there, outside. This is not about, this Widmer is so good because it's really not about Fujiki class C, although it would seem so at first. And it's very late, thank you very much.